Have you ever looked up at the stars and wondered about time? We think of it as a constant, a river flowing at the same speed for everyone, everywhere. Tick-tock, 1 second after another marching forward into the future. But what if I told you that this idea, this comfortable human perception of time, is not the whole story? What if the universe has a secret that connects the force that keeps your feet on the ground to the very flow of time itself? Why does gravity, the invisible tether holding planets in their orbits and galaxies together, make time go slower? This isn't science fiction. It's a fundamental truth of our cosmos. This question isn't just a curiosity, it's a doorway to understanding the true nature of reality. It challenges our most basic assumptions about the world we live in. We experience gravity every moment of our lives. We feel its pull when we jump, when we lift a heavy object, when we simply stand still. It's so familiar that we barely notice it. But this everyday force is doing something extraordinary. It is actively warping, stretching, squeezing the very fabric of existence. It is whispering to the clocks of the universe, telling some to tick faster, telling others to tick slower, all depending on where they are. The universe is far stranger and more wonderful than we can possibly imagine from our little perch on this planet. For centuries we thought we knew gravity. Sir Isaac Newton gave us a simple law. He said gravity is a force, an invisible pull between masses. The Earth pulls on the moon, the sun pulls on the Earth. An apple pulls on the ground just before it falls. This idea worked wonderfully. It let us predict planetary motion, it let us calculate the tides, it let us send the first rockets toward the heavens. Newton's gravity governed the cosmic dance, but the picture had cracks. Newton was puzzled. How could this force act instantly across empty space? How did the sun know where the Earth was? It felt like a ghost in the machine, a mysterious action at a distance with no mechanism. For over 200 years that mystery stood. We had the what, the law, but not the how. The universe was hiding a deeper secret. Then a century ago another brilliant mind arrived. He reshaped our understanding. He showed that gravity wasn't a force at all. This new vision was one of history's greatest leaps. It forced us to abandon the invisible rope idea. Instead, space itself isn't an empty stage. The answer wasn't a force, but a shape. To understand this new idea of gravity, we first need to meet its main character, space-time. Think about how you describe an event. You say where it happened, at the corner of 5th and Main, and you say when it happened, at 3 o'clock in the afternoon. You need both location, which is space, and a moment, which is time, to pinpoint any event in the universe. A young Albert Einstein realized that these two things, space and time, were not separate. They were intimately woven together into a single four-dimensional continuum. He called it space-time. It's the stage on which all the events of the universe unfold. Imagine a giant, flat, stretchy sheet of rubber. This sheet represents space-time. In a universe with nothing in it, the sheet would be perfectly flat and undisturbed. If you roll a marble across it, it will travel in a perfectly straight line forever. Now, let's place something on our rubber sheet. The bowling ball sinks into the sheet, creating a deep curve, a depression in the fabric. The sheet is no longer flat. So what happens now if we roll another smaller marble near the bowling ball? It will no longer travel in a straight line. This, Einstein said, is what gravity is. It's not a force, it's the geometry of space-time. Albert Einstein's journey to this conclusion is a story of pure thought. He conducted what he called thought experiments, imagining scenarios to push the laws of physics to their limits. One of his most famous thought experiments involved an elevator. Imagine you are in a windowless elevator cabin floating freely in deep space far from any planet or star. You would be weightless, drifting around. Now imagine a cable is attached to the top of the elevator and it starts pulling you up with a constant acceleration. You would suddenly feel your feet pressed against the floor. If you dropped a ball, it would fall to the floor, just as it does on Earth. Inside this windowless box, you would have no way of knowing whether you were being accelerated through space or were simply sitting still on the surface of the Earth. Einstein called this the principle of equivalence. The effects of gravity are completely indistinguishable from the effects of acceleration. This simple but profound idea was the key that unlocked the entire mystery. If gravity and acceleration are the same, then whatever is true for acceleration must also be true for gravity. And something very strange is true for acceleration when it comes to time. Let's go back to our accelerating elevator. Imagine a beam of light is sent from one side of the elevator to the other. Because the elevator is moving upwards, by the time the light reaches the other side, the wall will have moved up slightly. To an observer inside the elevator, the light beam would appear to bend downwards, as if it were being pulled by gravity. If gravity and acceleration are equivalent, then gravity must also bend light. And if acceleration is equivalent to gravity, then the same must be true for gravity. A clock in a stronger gravitational field must tick slower than a clock in a weaker one. So, Einstein's theory of general relativity, published way back in 1915, made these two, pretty wild predictions. Gravity bends light, and gravity slows down time. At first, these ideas were just that, ideas born from thought experiments. They were beautiful and elegant, but, science demands proof. It demands evidence from the real world. The first great test came just a few years later in 1919. A British astronomer named Sir Arthur Eddington led an expedition to observe a total solar eclipse. The goal was to see if the sun's gravity really could bend the light from distant stars. During a total solar eclipse, the moon blocks the brilliant light of the sun, which allows us to see the stars that are in the sky near the sun's position. Eddington and his team photographed the star field around the sun during the eclipse. Then, they compared these photographs to pictures of the same star field taken months earlier, when the sun was in a different part of the sky. If Einstein was right, the stars closest to the sun's edge during the eclipse should appear, well, just slightly out of place. Their light, on its long journey to Earth, would have been bent as it passed through the warped space-time around the sun. The results were, honestly, astonishing. The measurements from the eclipse expedition confirmed Einstein's prediction almost exactly. The stars did appear to shift. The news made headlines around the world. A new vision of the cosmos had been confirmed. The universe was not the clockwork machine of Newton. It was a dynamic, curving, twisting landscape of space-time. Gravity was indeed geometry. This single observation, made by looking at the faint light of distant stars, forever changed our understanding of the universe and made Albert Einstein a global icon. One of the first and most elegant confirmations didn't require rockets or spaceships. It just required a mountain and some very, very good clocks. The experiment is wonderfully simple in its concept. According to Einstein's theory, the strength of gravity gets weaker the farther you are from the center of the Earth. This means gravity is slightly weaker at the top of a mountain than at sea level. Therefore, a clock placed at the top of a mountain should tick just a tiny bit faster than an identical clock at the base. In 1959, physicists Robert Pound and Glenn Rebka designed a clever experiment at Harvard University to test this very idea. They didn't use a mountain, but a tower. They placed a source of gamma rays, a kind of high-energy light, at the bottom of a 22.5-meter-tall tower, and a detector at the top. According to relativity, the light waves should be slightly stretched as they travel uphill against Earth's gravity, arriving at the top with a slightly lower frequency, a phenomenon known as gravitational redshift. This is a direct consequence of time running slower at the bottom than at the top. The clock at the bottom is ticking slower, so it emits fewer wave crests per second than the clock at the top would measure. The effect was incredibly small, but their instruments were sensitive enough to detect it. The results matched Einstein's predictions perfectly. It was a direct measurement of gravity's effect on the flow of time, right here on Earth. Later, more direct experiments were performed. In 1976, scientists launched a rocket carrying a highly accurate atomic clock to an altitude of 10,000 kilometers. They compared its ticking rate to an identical clock on the ground. After its 2-hour flight, the clock on the rocket was found to have gained about 47 microseconds compared to the ground clock, exactly the amount predicted by relativity. These experiments are not just academic curiosities, they have a profound impact on our modern world. The Global Positioning System, or GPS, that your phone uses to tell you where you are relies on this principle. To truly grasp the strangeness of time dilation, let's turn to another of Einstein's famous thought experiments, the twin paradox. Imagine a pair of identical twins. Let's call them Stella and Tara. Stella is an astronaut. Tara is a scientist who stays on Earth. On their 30th birthday, Stella embarks on a journey to a nearby star in a super-fast spaceship, traveling at nearly the speed of light. Tara stays behind on Earth. From Tara's perspective on Earth, she watches her sister's clock tick much, much slower as she speeds away. Years go by for Tara. She celebrates her 40th birthday, her 50th birthday, her 60th birthday. She continues her work, grows older, and watches the world change. Meanwhile, in Stella's spaceship, time is passing much more slowly. For her, the journey to the star and back might only take a few years. Finally, Stella's ship returns to Earth. As she steps out of the spaceship, she is in for a shock. The world she left has changed dramatically. She finds her twin sister Tara is now an old woman. While only, say, 5 years have passed for Stella, 50 years have passed for Tara on Earth. Stella is now biologically much younger than her own twin. The twin paradox shows us something incredible. Time travel to the future is not just possible, it happens all the time. Every time an astronaut orbits the Earth, they are traveling into the future at a slightly faster rate than the rest of us. The effect is tiny, almost unnoticeable, but it is real. To make the effect more dramatic, you just need to ramp up the two things that warp time: speed, gravity. If you want to jump far into the future, you need to either travel very close to the speed of light, or spend some time in a very strong gravitational field. Let's focus on gravity. The most extreme gravitational environments in the universe are found near black holes. A black hole is what's left behind when a very massive star collapses under its own gravity. A black hole is like a bottomless pit in the fabric of space-time. Imagine a future mission where a brave crew takes a spaceship and orbits a supermassive black hole, like the one at the center of our Milky Way galaxy. Here, time is slowed to a crawl. For every single hour that passes for the crew on the ship, thousands of years might pass for the rest of the universe. They could orbit for what feels like a few years, watching the distant galaxies wheel by in a cosmic ballet. When they finish their mission and fire their engines to return to Earth, they would return to a world that is tens of thousands of years in their future. The universe has a built-in mechanism for forward time travel. The only catch is, it's a one-way trip. There's no known way to go back. We have journeyed across the cosmos from the mind of Einstein to the edge of a black hole. We've seen that gravity warps the very fabric of reality, bending light and, most astonishingly, slowing the passage of time. This isn't some abstract theory that only applies to distant galaxies or futuristic spaceships. It's happening right here, right now, all around you. The effects are incredibly subtle on our human scale, but they are always there. The cosmos is a far more wondrous and strange place. The force of gravity is slightly stronger at your feet than it is at your head, because your feet are closer to the center of the Earth. This means that time is ticking just a tiny, tiny bit slower for your feet than it is for your head. The difference is infinitesimal, something like a few billionths of a second over your entire lifetime. You will never ever be able to notice it, but it's real. Your head is aging ever so slightly faster than your feet. We are all living, breathing time machines, stretched out in time from top to bottom. This fact may seem trivial, but it speaks to a profound truth. The laws that govern the orbits of giant stars and the bending of light from distant quasars are the same laws that are at work within your own body. You are not separate from the universe, you are a part of it. The cosmic dance of space-time is happening not just out there, but in here. Every step you take, every breath you draw, you are interacting with the fundamental geometry of space and time. The universe isn't a distant spectacle to be observed, it's the very stage on which our existence plays out. So the next time you feel the pull of gravity holding you to the Earth, remember what it's really doing. It's not just a force, it's the shape of your reality. The universe is whispering a secret to you every moment of every day. Time is not what it seems.